Svi studenti, popis je istre, vidjeli ste ga.
Možete i sa
Nešto ja ću jel se čujemo gore? Super, ja ću ovak ili...
Da, možemo još pričati. Ovo ćemo za publiku na posljednju. Evo sad smo na YouTube. Sad je tu ili tu sam. Stavio dva usera iz režije ovaj krp. Ok.
Možemo početi.
Dobar dan svima. Ja ću vas samo kratko na početku pozdraviti na početku ove sekcije predavanja. Hvala što sudjelujete na ovim predavanjima u sklopu festivala znanosti. Pa evo, Sanja, ćeš ti nešto prije?
Pa evo, ja bih vas isto pozdravila drugi dan festivala. Hvala svima što ste došli. Danas imamo ovaj ciklus znanstveno-popularnih predavanja, 5 predavanja koja nam idu i live se streamaju na YouTube mreži, tako da ćemo nastaviti biti u rasporedu. Ja bih, evo Mladena, ako imaš još nešto, ako ne, najavila našeg prvog predavača.
Naš prvi predavač je magistar Ivan Palijan iz tvrtke Palijan d.o.o.
Evo, magistar Ivan Palijan je ovlašteni inženjer građevinarstva, projektant, završio je 2011. godine građevinski, magistrirao je na Građevinskom fakultetu u Zagrebu. Danas je naš doktorand, ima svoj ured za projektiranje građevinskih konstrukcija, dobitnik je nagrade Polos 2018. godine za konstrukciju Grand Park hotela Rovinj. I evo, danas će nam prezentirati zgrade gotovo nulte energije, pa Ivane, izvolite.
Hvala vam lijepo, hvala na lijepom predstavljanju. Poštovani studentice i studenti, poštovane profesorice i profesori, poštovane kolegice i kolege, sve vas lijepo i srdačno pozdravljam. Evo, kao što ste čuli, znači ja sam Ivan Palijan, zadnjih 20 godina vodim svoj projektantski ured. Ja i moje kolege smo u tih 20 godina u suradnji sa vodećim hrvatskim arhitektima imali prilike projektirati puno ili dosta značajnih građevina u Hrvatskoj, poput stadiona Rujevice u Rijeci, poput hotela Park u Rovinju ili zgrade Infobipa u Zagrebu. Tema mojeg današnjeg predavanja su znači zgrade gotovo nulte energije, proizvedene na industrijski način, što je isto imeni i naziv projekta kojeg sufinancira Evropska unija, a provodi tvrtka Tehnoplast Profili iz Zagreba u suradnji, odnosno sa svojim partnerima, Građevinskim fakultetom u Rijeci i mojim uredom projektantskim. Tehnoplast kao tvrtka već niz godina razvija i proizvodi zapravo zgrade koje se proizvode u tvornici do nekakvih, mi bismo htjeli do 90% gotovosti, a sada smo otprilike na nekih 60%. Takve zgrade, znači, poput automobila ili mobitela se proizvode u tvornici, znači na način da je nosiva konstrukcija od tankostijenih čeličnih C profila koji se onda sklapaju u pogonu u panele u koje se predmontiraju sve instalacije, prozori, vrata i onda kao što na ovoj slici ovog animaciji pokazuje se, dolaze kao gotove na gradilištu. To je, ovo ide u drugom smjeru, ja sam htio ovo. Inovativnost ove tehnologije, znači, očito su u fazi građenja, u fazi projektiranja i u fazi, znači, ekologije. U projektiranju, znači, ostvarujemo povoljan omjer između neto i bruto površine takvih zgrada, zato jer u jednom tankom zidu koji je bitno tanji od nekakvog zida koji se radi u klasičnom načinu građenja, imamo i toplinsku izolaciju, imamo i nosivu konstrukciju. Ono što bih htio isto tako naglasiti da smo u mogućnosti izvesti svaku arhitektonsku formu, svaki arhitektonski koncept, građevine, bilo to obiteljska kuća, hotel, bolnica, škola, isto tako i svaki dizajn eksterijera i interijera. Što se tiče otpornosti na potres, tu postižemo značajne dobre rezultate, zapravo jer zgrade koje se grade i proizvode na ovaj način su male mase, a zapravo djelovanje ili učinak potresa je proporcionalan masi zgrade, pa znači ako smo smanjili masu zgrade, najviše smo doprinijeli otpornosti na potres. Naravno, zbog dobre toplinske izolacije tvrdimo da su to zgrade gotovo nulte energije, potrošnje energije. U građenju je zanimljivo da cijelu zgradu zapravo, to želim istaknuti, izvodi jedan izvođač koji proizvodi sve dijelove za tu zgradu, od panta do nosive konstrukcije. Isto tako, onda projektni tim izvođača u jednom modelu, jednom BIM modelu izrađuje sve radioničke nacrte, znači nosiva konstrukcija, fasada, stolarija i sve izvodi taj jedan izvođač, pa tu na taj način znači smanjujemo mogućnost bilo kakve greške koje su kod drugih načina građenja gdje danas na primjer građenju i obiteljske kuće ili hotela sudjeluje barem 40 različitih struka koje je vrlo teško međusobno uskladiti. Na ovaj način se takve usklađenje i koordinacije zapravo izbjegavaju ili nisu bitne. Naravno, takav način građenja pridonosi onda lakšoj kontroli kvalitete, sigurnosti i svemu što zgrada treba zadovoljiti. Ako bismo prema jednom projektu imali priliku izvesti više zgrada, to bi se naravno odrazilo i na cijenu takve kuće ili bilo koje druge građevine. Ova tehnologija građenja sigurno i u skladu sa cirkularnom ekonomijom ili politikom cirkularne ekonomije, jer cijeli postupak građenja je suh, svaka zgrada može se demontirati i montirati i po potrebi preseliti na drugu lokaciju. Isto kad govorimo o trošenju energije, ako nešto proizvedemo u tvornici, zapravo mi na jednom šleperu možemo na gradilište otpremiti u jednom transportu cijelu zgradu, na primjer obiteljsku kuću od 100 kvadrata. Dok sigurno da trošimo onda manje energije nego da svaki pojedini materijal, beton, vozimo 10 puta. U svrhu znači poboljšanja i valorizacije temeljnih zahtjeva za građevinu, kao što su mehanička otpornost i stabilnost, sigurnost u slučaju požara, zaštita od buke i gospodarenje energijom i očuvanje topline, znači provodi se dva znanstveno-istraživačka projekta, trenutno su u toku, u suradnji znači sa Građevinskim fakultetom, vašim Građevinskim fakultetom u Rijeci, sa ciljem poboljšanja mehaničkih i toplinskih svojstva građevine, projekt pod nazivom Predgotovljene zgrade gotovo nulte energije proizvedene na industrijski način. A u suradnji sa Građevinskim fakultetom u Zagrebu istovremeno sa ciljem provjere poboljšanja otpornosti na požar te zaštite od buke i gospodarenja energijom, projekt pod nazivom Kompozitni lagani panel sa integriranom nosivom konstrukcijom. U okviru ovog našeg projekta sa vašim Građevinskim fakultetom Provedena su trenutno ispitivanja, znači komponenti kompozitnog panela sa integriranom čeličnom jezgrom. Najveća nepoznanica u tom našem kompozitnom panelu je polimerna pjena, za koju imamo najmanje dosad istraženih podataka iz literature, pa smo između ostalog tu posvetili najveću pažnju možda na istraživanju svojstava, mehaničkih svojstava polimerne pjene. Takav naš kompozitni lagani panel sastoji se od 3 glavne komponente. To je vanjske obloge od montažnih vlaknastih ploča, zatim jezgre izrađene od otvorenih tankostinih čeličnih C profila i ispune od polimerne pjene. Zadaća ovih gips vlaknastih ploča je u prvom redu otpornost od požara, to je njihova primarna uloga. Čelični C profil je u službi ili u svrhu, znači, mehaničke otpornosti i stabilnosti, a polimerna pjena najveće doprinosi toplinskoj izolaciji ili očuvanju energije. Naravno, mi bismo htjeli ići korak dalje, a to znači da bismo htjeli postići dobru prionljivost između polimerne pjene i tankostinih C profila, isto tako prionljivost između polimerne pjene i obložnih ploča, čime držimo da bismo dobili zapravo spregnuti presjek ili spregnuti materijal, spregnuti kompozitni panel, gdje bi onda sve ove 3 komponente sudjelovale ravnopravno i doprinosile otpornosti nas, na primjer, ako je opterećenje okomito na ravninu takvog panela, otpornosti na savijanje, ako je opterećenje u ravnini takvog presjeka, otpornosti na uzdužnu silu. Znači, znamo svi da je kruto se povećava bitno odnosno najviše doprinosi statička visina. Ako smo ova 3 materijala spregnuli jedan, to smo sigurno postigli taj efekt, znači krutosti i povećane nosivosti. Znači, sljedeća istraživanja u sklopu ovog projekta, a zapravo i teme doktorskih radova koji će, nadam se, iz njih proizaći, je ovo što sam već zapravo na neki način rekao: otpornost na savijanje i poprečnu silu okomito na ravninu kompozitnog panela, zatim otpornost na uzdužnu i poprečnu silu u ravnini panela i otpornost priključaka, znači stropnih nosača na zidne panele. Što se tiče, znači, otpornosti na savijanje, očekujemo i, znači, predmijevamo da će se bitno povećati, znači, takva otpornost u odnosu na otpornost samo čeličnog profila ili poprečnog presjeka u smislu otpornosti na savijanje. Rezultat ovih naših istraživanja bi trebale biti praktične formule koje će služiti onda inženjerima u praksi, u projektiranju, da mogu na vrlo jednostavan način primijeniti ovaj kompozitni panel u smislu, znači, nosivosti koje je okomito na ravninu takvog panela. Što se tiče otpornosti na uzdužnu i poprečnu silu u ravnini kompozitnog panela, svjesni smo da nas tu očekuje vrlo složena priprema, znači, samog eksperimenta, u smislu da istovremeno moramo opterećivati naš uzorak sa uzdužnim opterećenjem, odnosno opterećenjem u ravnini tog zidnog panela i sa horizontalnim opterećenjem, a da se pritom ne umanji efekt tog horizontalnog nanosa, znači, ili unosa sile i pomaka u sami panel. Biće zanimljivo. Kad govorimo, znači, o priključcima, znamo da svaki konstruktivni sklop zapravo ovisi o priključcima. Priključci su nekako možda najzanimljiviji dio, a možda i najteži i vama možda kroz studij, a i nama kasnije u praksi. Znamo da tu moramo posvetiti maksimalnu pažnju. A u ovoj situaciji, kad imamo ove naše tankostine C profile, spojiti njih, pa na primjer kao u ovoj skici gore desno, imam i laser, gore desno, gore desno, znači kad imamo stropni nosač koji bi trebao biti kontinuiran preko zidnog panela, a u tom zidnom panelu je vertikalni konstruktivni element ili stupac, da to nije lako ostvariti. Zato imamo ovdje pomoć ovih naših ispričavam se. Ovih naših spojnih elemenata, ili kraće rečeno spojnica, koje ne omogućavaju da ovaj tankostivni profil na koji priključimo spojnicu sa, na primjer, vicima M6, da dovedemo se u situaciju da dalje radimo priključak kao sa valjanim profilima, gdje onda vicima M12 međusobno spajamo i u mogućnosti smo onda primijeniti metodu komponenata na način da istražimo ponašanje svake od tih komponenti u zoni, znači vlačnog djelovanja, tlačnog djelovanja i posmičnog djelovanja, da istražimo preko radnih dijagrama sila pomak, da istražimo njihova svojstva, da usporedno napravimo i numeričke modele, da možemo znači uspoređivati rezultate laboratorijskih ispitivanja sa rezultatima numeričkih modeliranja, međusobno to kalibrirati i dobiti opet cilje da dobimo praktične formule, jednostavne formule koje bismo mogli onda primjenjivati u svakodnevnoj inženjerskoj praksi. Naravno, u svakodnevnoj gradnji znači moramo imati uredno napravljene nacrte montaže da bismo mogli na gradilištu smontirati naše konstruktivne slopove. Takvi nacrti se redovito sastoje od lista ovoga konstruktivnih elemenata od kojih se sastoji zgrada. Sastoji se, mora biti pozicioniran svaki konstruktivni sklop kako dolazi na svoje mjesto i kako se međusobno spaja da bi se na gradilištu što jednostavnije moglo sklopiti. Prije toga moramo izraditi radioničke nacrte sa svim pozicijama koje ulaze u sklop, na primjer ovdje prikazanog zida, kao što su sami čelični elementi, spojnice, čvorni limovi. Znači da bi se svaki od tih elemenata mogao izraditi na CNC strojevima, mora biti prije toga precizno nacrtan i izmodeliran. Bilo da je riječ o zidu ili, na primjer, rešetki kao stropnom ili krovnom nosaču. Isto tako, znači, spajanje i detalji spajanja već prije spomenuti onim numeričkim modelima ili mehaničkim modelima, a ovako to izgleda u stvarnosti. Tu želim reći da znači ovakovi detalji nam omogućavaju znači da možemo praktično primjenjivati ove naše tankostivne C profile. Na gradilištu, kad dođemo na gradilište, izgleda ovako, znači ovdje je prikazan, odnosno vidi se na ovoj fotografiji montirani dva zida spojena u uglu, u njih su na gradilište došli već predmontirani prozori, sve izbušene rupe kroz čelične nosače za uvlačenje instalacija. Evo, tako to izgleda na gradilištu. Sada, znači, mogu vam dalje pokazati neke od izvedenih građevina koje smo imali prilike u zadnjih nekoliko godina izvesti i realizirati. Na ovoj slici je prikazana znači AC Marina u Splitu, zgrada od nekih 1000 kvadrata sa nekoliko prizemnih dijelova, troetažnom osmatračnicom. Sve što vidite na ovoj slici, znači proizvela jedna tvrtka od rukohvata, ograda, znači stubišta, ventiliranih fasada, staklenih stijena, znači ono što je prednost takvog načina, što sam već prije rekao, je da nije trebalo gotovo 6 mjeseci koliko smo to gradili, nije trebalo ni jedne gradilišne koordinacije, jer se sve proizvelo u jednoj firmi na istim strojevima. Obiteljska kuća, možda jednostavnog vanjskog dizajna, ali želim istaknuti da također i sve staklene vrata, interijer je također predmet građenja. Ja bih rekao da mi pokušavamo raditi ono što je radio nekad Michelangelo, da jedan čovjek ili jedna firma izvodi cijelu kuću. Kuća sljedeća u Fažani, arhitekt Bruno Jurčić, 66 ploha u fasadi, kamena fasada sa minimalističkim fugama od 2 mm, opet staklena, ogledna staklena stijena. Ovaj krov nek vas gore ne buni, to je zbog urbanizma, vjerojatno će se jednog dana maknuti pa će bolje izgledati. Ovo nije Photoshop, ovo je sa dronom snimano. Ok, Vila Šolta, to je kuća koju sad gradimo, znači sa kamenom fasadom, ventiliranom kamenom fasadom, ograda suhozid. Prekrasan pogled, arhitekti su baš jako sretni što su uspjeli investitoru pružiti ovaj divan pogled na more. Moji kolege iz Tehnoplasta su isto tako presretni jer su uspjeli konstruirati, razviti, napraviti ovu kliznu stijenu koja se eto ovako prekrasno pomiče, minimalno ima aluminijskih elemenata, a nama projektantima konstrukcije isto jako drago što smo uspjeli riješiti i ostvariti sve te ambicije arhitekata, što kuća baš tamo gdje bi trebala imati zidove nema ih. Naravno, to se sve može riješiti, znači mislim da u fazi, odnosno da mi kao projektanti konstrukcije, znači moramo samo dovoljno razgovarati s našim kolegama arhitektima i držim da se svaka situacija može riješiti na jedan dobar način. Ovdje smo umjesto onih tankostjenih profila C koji sam do sad pričao, upotrijebili naravno valjane HEP 100. HEP 100 je još uvijek mali profil prema 1000, ali ima 23 cm kvadratnih površinu, dok onaj C profil ima stvarno 2 cm kvadratnih. Ali je dobro došao, znači ovdje da smo napravili jednu ravninsku rešetku u jednom i drugom zidu i riješili to na način da u uglu je ovaj prekrasan otvor. Kuća koju smo prošle godine napravili u Poreču, znači tipologija za Valamar, ne znam, smijem reklamirati, ali dobro. Smještene jedinice, znači od 35 kvadrata, znači tipologija hotela ili ti soba na otvorenom. Znači ovo sve što vidite tu je sagrađeno na gradilištu u 7 dana. Prije toga smo to proizvodili u tvornici i dovezeno je u srijedu ujutro na šleperu u 8 sati je došlo na gradilištu. Utorak smo zbetonirali temelje, znači temelji su za ovakve zgrade koje zapravo su teške oko 150 kg po metru kvadratnom, a za usporedbu kuća sa armiranom betonskom nosivom konstrukcijom je otprilike 1000 kg po metru kvadratnom. Znači temelj je tu ploča 20 cm, to smo znači utorak zbetonirali, u srijedu smo stavili ujutro hidroizolaciju, izbušili anker, istovarili sa šlepera znači 4 zida i gore krovnu konstrukciju. Ok, trebalo nam još nekoliko dana da završimo do kraja interijer i eksterijer, ali zapravo zidovi su došli s ovim keramičkim pločicama i sa unutra sa obložnim pločama. I ovako je to izgledalo nakon 5 dana. Obiteljska kuća u Zagrebu, zanimljivo je to da je izvedena prije potresa koji se dogodio u Zagrebu i znači nije pri potresu pretrpjela nikakva oštećenja. To je potvrda onog što sam prije rekao da gradimo sigurne kuće. Toliko od mene, hvala lijepo.
Hvala, Ivane. Evo imamo vremena za pitanja, pa slobodno vjerujem da ima.
Slobodno pitanje. Sad mi je puno lakše, ne moram da sve.
Ja ću vas pitati koje su ograničenja što se tiče katnosti, do kojeg kata se može vratiti?
Samo mašta granica.
Samo mašta.
Naravno, sad će biti ozbiljan, ispričavam se. Znači, možemo napraviti ono, zapravo, nismo ograničeni, ja bih rekao, ako ovdje govorimo o tehnologiji građenja, da su to samo tankostini C profili koji, ponavljaju, imaju samo 2 cm kvadratna. Znači, sa time možemo sigurno 3-4 etaže napraviti bez problema, to sada mislim. Ali možemo dalje kombinirati sa i ostalim valjanim profilima i osmišljavati konstrukcije koje će moći imati veću katnost, gdje će možda sa mikrospregnutim stupovima, sa jezgrama koje će biti B-stil, svi smo čuli za to, koje su punjene nekim mortom za injektiranje, pa onda sa nekim opet prilagođenim podlakama, a dalje ovakvi rešetkasti nosači mogu biti na 1. i na 10. etaži. Tako da sam ja tu vrlo ambiciozan i mislim da ćemo moći graditi na ovaj način sve zgrade.
A da ste samo do 3. tako?
A to smo do sad radili 3 etaže.
Kako se uspoređuje financijski takva investicija s obzirom na klasičnu gradnju?
Ovako, znači, ja bih vam rekao da svaka kuća isto otprilike košta. Bilo konstrukcija ovakova ili onakova. Znači, mi kažemo da kuća građena na ovaj način košta jednako kao i kuća koja ima armiranom betonsku konstrukciju, ciglenu ili, na primjer, drvenu. Zapravo, na kraju krajeva cijenu određuje da li je to 1200, 1300 ili 2000 eura po kvadratu, to su neke uobičajene, ako govorimo cijene o obiteljskih kuća, ali pritom govorim da je to cijena znači kuća useljiva, znači sa svim instalacijama, sa svim pločicama, samo treba unijeti namještaj. A da li košta više, toliko vas košta bilo na koji način ugradite, ako ste sve platili. U smislu da, znači, kažem, to je cijena kuće po kvadratu, znači bilo koji materijal. Mi samo mislimo da možemo kvalitetnije napraviti od možda na ovaj drugi način građenja. Najskuplje je u kući zapravo i unutarnje uređenje, da li imali skupi parket, pločice ili nekakvu sanitariju, pa se onda može popest cijena i na 3-4 tisuće. Ali u usporedbi je to slična cijena na bilo koji način gradnje.
Znači, najveća prednost je brzina gradnje.
A brzina gradnje, da, samo naravno moramo se prije toga dobro pripremiti, da bi brzina gradnje bila takva kakva je. U svakom slučaju, da, brzina i preciznost gradnje.
I ono što smo na početku imali, zelena gradnja, otpornost na potrese,
da. I mogućnost izvedbe, znači što sa industrijom baš i nije, bilo bi bolje da po jednom nacrtu izvodimo 100 jednakih kuća nego da izvedemo samo jednu kuću, ali na ovaj način mislimo da smo razvili tehnologiju kojom onda možemo dati odgovor na svaki zahtjev.
Možda još pitanje?
Evo, hvala na prezentaciji. Zanimljivo, ja sam pitala kako stojite sa zaštitom buke i to je još uvijek u fazi ispitivanja odnosu na klasičnu gradnju. To je masivno zapravo povoljno. A ovdje je sama konstrukcija laganja.
Da, slažem se s vama da...
To je aspekt koji je zapravo neka ugoda. Estetika je definitivno zadovoljena, ali isto kvalitete življenja.
Slažem se s vama da za udarni zvuk je jako bitna masa koju ovdje nemamo, ali zapravo prodor zvuka kroz zid se može i riješiti na drugi način, da imamo različite materijale, pa se taj zvuk onda zbog različitih valova i frekvencija znači prekida. Znači, može se postići dobra zvučna izolacija. i radimo na tome. Isto tako smo u fazi, ovo što sam rekao, drugog KIRI projekta koji se bavi baš tim pitanjem. Znači, kroz upotrebom različitih materijala i pravilnom gradnjom nadoknađujemo tu možda malo što imamo manju masu.
Ali znači, računate da ćete doći do nekakvih vrijednosti?
Pa ne, računamo. Sigurni smo to da ćemo imati decibela koliko smijemo imati da bi se u toj kući ugodno živjeli. I to smo već isprobali u praksi.
Možda još jedno ili dva pitanja koje imamo.
Evo, ja bih se osvrnuo na ovaj dio sa istraživanjem na fakultetu. Vi ste rekli da je vama cilj kroz istraživanja doći do nekih konačnih formula, empirijskih, recimo da bi nekakav inženjer koji mogao primijeniti te formule. Mene zanima koja je zakonska procedura ili otprilike od istraživanja do gotove formule primjenjive u praksi.
Pa evo, ja sam to rekao u skraćenoj verziji. Znači, svaki inovativni proizvod koji dolazi na tržište kao neka novina mora proći tu fazu istraživanja, fazu doktorata i doći do tehničkog dopuštenja. Nakon tehničkog dopuštenja ulazi u propise kao dio propisa. To je neki put. Naravno, mislim da to ne sprječava da se takovi proizvodi inovativni već i u ovoj fazi primjenjuju. Za sada mi projektiramo i gradimo u skladu sa, kad govorimo o nosivoj konstrukciji, prema Eurokodu 3, odnosno hrvatskoj normi za nosive konstrukcije. Sam sam bio u prilici primijeniti, na primjer, davno, ne tako davno, spregnute stropne ploče koje je tada Arcelor za njih, za te limove, znači kao patent imao tehnička dopuštenja i čak i prije tehničkih dopuštenja. Pa tako i u ovom našem slučaju, put je taj koji sam prilike rekao.
Ko daje tehničko dopuštenje?
Tehnička dopuštenja daje ovlašteno tijelo, znači u svakoj državi. Pa sada je to na nivou Europske unije.
Možda još jedno kratko pitanje. Evo, ja bih se ovdje zahvalila Ivanu Palijanu za ovo predavanje. Hvala vam, bilo izvrsno, ja vjerujem da imam još pitanja, ali da ne kasnimo s ostalima, možete onda možda i poslije, ako vas uhvatimo, ako nam ne pobjegnete.
Hvala vam lijepo što ste me pozvali, bila mi je iznimna čast i zadovoljstvo družiti se s vama, ja se nadam da neće biti zadnji put.
Ja se nadam, hvala. Evo, ja bih onda najavila našeg sljedećeg predavača. To nam je naš isto tako doktorand Schira, ja ga pozivam da nam se pridruži ovdje. Znači, nakon završenog studija brodogradnje i građevinarstva, karijeru započinje u kompaniji za razvoj infrastrukture za eksploataciju nafte i plina u podmorju, te zatim prelazi raditi za izvođača pri izgradnji obalnih vjetrofarmi. Trenutno radi za inženjersku konzultantsku firmu koja se bavi vjetroparkovima i, kao što sam već rekla, naš je student. Danas će nam prezentirati predavanje Offshore Wind Farms koje će održati na engleskom jeziku. Pa evo, lijepo je ovo vaše.
Hello to everyone. My name is Vivoda Prodan. I'm a chartered civil engineer, and I'm working for a consultancy company called G003 Solution that we have offices in Ireland and in the UK, and we are supporting the wind farm construction business. So today I will be talking just a little bit about offshore wind farms in general terms. So offshore wind, where we currently, the estimation is that we have installed globally around 25 gigawatts. For comparison, like we have a thermal power plant here in Plomin, Luka, where the total installed power was before I think the total capacity was around 340 megawatts. So where are we heading actually? The aim is up to 2050 to get installed more than 500 gigawatts. Only European Union, who is leading in this, Europe as a whole, because actually Britain is leading, has the plan to have more than 60 gigawatts installed by 2030 and 300 by 2050, which is like, the market is growing around 25% yearly so far. So how much actually we can, what is the potential of the wind? So potential of the wind actually depends on the technology we are using in the wind turbines, but currently it's estimated about 420,000 terawatt hour. So this is like more than 80 times the global electricity demand consumption today. And for example, Croatia, just for to compare, consumes around 18 terawatt hours gross per year. And why offshore wind? Because this chart actually shows nicely why offshore wind. The wind speeds are more steady and they are higher on average offshore than on land. And this is why, and see where it's actually the best parts are here, and actually UK already, as I said, they are leading in this. Where is Croatia here? Well, actually we have 4 gigawatts approximately of fixed foundation turbines available here south of Pula, and there is some potential here. Okay, this is not the real potential, because the real potential depends on other things like marine traffic and things like that. So this is just a theoretical potential so far. In total 17 gigawatts. So the evolution of wind turbines, for example. So the wind turbines, they started as very small ones. When I entered the industry, it was here around 2015. Actually, mostly they were 5 to 6 megawatts. Now the latest installed one and in operation, it's in Netherlands, it's 11 megawatts, and they are currently testing 14 megawatts. And we now, when we are planning the new wind turbine sites, offshore wind sites around Ireland, we are planning to have 24 megawatts, which is not even in development yet. But in 10 years' time, this can be the case. And why are they getting bigger? Actually, because the power equation actually tells us that there is a coefficient of how much climatic energy from the wave we can get, and this is all fixed, and practically the wind speed is fixed. It can just a little bit rise as we are going higher with the wind turbine tower, but actually by changing the diameter, we are getting more power. So this is why they are getting bigger and bigger. So this is like currently, you see, it's like around 230 meters diameter of the wind turbine. So just a nomenclature. So this is how the typical layout looks like. We have and what we say offshore is this part, obviously, and onshore is that part. And I'm mainly working on this part. Here we have wind turbine foundations and turbine generators. They are connected with the wind turbine inter-array cables. This is offshore substation because it's a transformer. It has a transformer that transforms the lower voltage to higher voltage export current. So this is the offshore substation. And then we have the export cable, and on land we have a transition joint bay, and it goes to onshore substation when again it's transformed. The power is transformed to distributed to the grid. So these are export cables. So we have either the export cables can be either AC or DC, or it can be a combination of that. So wind turbine, what it consists of? It's we have a foundation, a pile foundation. Normally this is a fixed one up to 30 meters. We have the tower, we have a transition piece. This is the substation. Normally it's the jacket with the piles, and then a substation here. And then we have the cable, 3 core cables with optical fibers inside. Okay, this is early concept. It can be vertical axis and horizontal axis turbine, but this is only used today. So this is just some pieces. It's like a protection for the scour, pile, transition piece, and wind turbine. This is a nacelle. This is our the blades, the tower. This is different turbine types depending on the water depth. So far, most of the more than 80% of the actually offshore wind farms use this one, a monopile foundation. But then we have a tripod, we have a jacket foundation up to 60 meters. We have a gravity-based foundation. It can be concrete or steel up to 20 meters, let's say. And for more than 60 meters water depth, we have floating wind. So far, only some we have only some have been installed in the world, just just to test offshore wind. So they are not commercial yet; they are still being developed. So the substation can also be fixed with on the monopile, on the jacket, or it can be floating. This is just a concept. They didn't develop it. It's not implemented yet. It hasn't been built. So the types of cables we have the inter-array cables connecting wind turbines. We have the export cables connecting the turbines or the offshore substation with the shore. And we have interlink cables connecting two substations offshore. In case of one fails, one can take part of the power. Why is there a difference? Why we are using actually the AC and DC cables? We are using them because AC cables are good up to a certain length from the shore. Because to have DC, all the wind turbines, they actually generate AC power. So we need a transformer offshore to convert it to the DC current to be able to export it to the shore. And the problem is that this substation is around 7 to 10% of the total investment, which can be billions of euros of the wind farm. So basically, up to 80 kilometers, let's say approximately, the AC cables are cheaper. Then the losses in the AC cable becomes higher than the investment costs of the transformer. What types of cables we have? We have a static cable, which has only one steel armor wire, and we have a dynamic cable, which has two steel armor wire. And this is specifically designed for fatigue. So these cables, we use them in floating wind, for example, in this suspended part. And so far, in all other wind farms that are not floating, static, fixed one, we use this one static that goes here just on the seabed, and we bury it below with special trenching tools. But this thing here is always moving, and this is why we need a heavy design. This is how it looks like. A cross section, 3 cores, and some optical fibers. Normally, the inter-array cables, they're all 33 kilovolts, and now they're becoming 60 kilovolts cables, and the export cables, they are between 120 and 400 kilovolts. And we have a dry, semi-dry, and wet design of the cable. So wet design means that the water can penetrate all the way to the core. This, for example, we have all sorts of other systems to protect the cable. This is a fixed foundation. This is the seabed. This is the scour protection, and this is a CPS, so-called cable protection system. Basically, the cable is being trenched here, but here we cannot trench it. So one part of the cable is exposed to the wave and current conditions, and is susceptible to fatigue. This is why we put it in these bend restrictors, actually to protect the cable. The design life of the wind farm is typically 25 years, as well as the cables. Typically, the stages of the wind farm development are those. This is let's say, based on the UK concept. So first, there is somebody, a governmental body, would check would make studies, numerical analysis, and measurements of the wind speed, and they would say which areas can be used for the wind development. Then they actually put a tender, and then the developers, they actually apply for the tender. They make their site assessment on their own to check which site they want, which is the best, most financially viable. Then they go into planning and development, engineering phase. Then it goes to, when the contractor is chosen, it goes to final design and construction phase, operation and maintenance, and at the end, the commissioning. We remove everything what we installed. So, for example, this is how it looks like. This is the 4th round in the UK, which is probably the most highly developed market in the world for the offshore wind. And they offered like these big areas to bid for developers. Developers check in each area what is the wind potential, and they bid for certain parts. This is the wind farm. Before we used just the layout of, before they were just put as a grid, but actually you have this wake effect, which is actually consuming the energy of the other wind farms. So nowadays they're using optimization techniques to actually optimize the layout of the wind turbines, so they actually maximize the energy extraction. Then we also do optimization of connections of wind turbines to minimize the losses in the cables. This is like construction of the wind farm. For example, there is a lot of survey, banking survey, geotechnical survey going on, boring, drilling, geophysical surveys before actually the construction phase, before the design even phase, detailed design, and then we go to the construction phase. Normally we use such a vessel, which can be floating vessel for pin pile installation, so for foundation installation, and then we use these vessels that are jacket vessels to install the tower and the blades and the nacelle. It takes around 1 day to install one turbine, let's say, more or less. And then we have the cable lay vessels, the cable lay vessels to install the cables. And I will just mention a bit the smart grids. So before, actually, the idea was, you had the energy producer and energy consumption, and actually the energy went only in one way. Nowadays, we are trying to optimize the grid so that actually the consumer also can become a producer by putting solar panels or something on your roof and things like that. So before we had only in one direction. Now there is a communication with all of them. And by implementing digital technology, AI, machine learning, digital twin, storing the data, control, automate the process, etc. By measuring information, monitoring, and predicting, we can actually optimize the consumption, and actually we can balance the energy supply with the energy demand. So before, for example, wind turbines were acting as an individual. Nowadays, there are already softwares that use machine learning and techniques like that. That actually automatically change the wind turbine blades orientation and the turbine orientation, so that actually they maximize the energy extraction of the whole wind farm. So it's not only about measuring one wind turbine, but how if we change the parameters of this wind turbine, we can actually increase the efficiency of the whole field. And then we are measuring also stresses, strains, and in the structures to be able to see how much fatigue life we consumed and what is the actually structural health of the structures. And nowadays, some new emerging technologies and advancements. For example, it's the biggest issue is the storage of the power, obviously, because we cannot control when the electricity will be produced, when will the wind blow. So how will we store this power to use in a later time? So we can do either power to X something conversion, so power to heat, to liquid, to gas, to mobility, to power. We can have this hub and spoke project, which is a huge project talk about later, and or offshore storage, so energy, hydrogen energy storage or compressed energy. So what we can do is basically we can generate the electricity, and then the extra electricity we can use to heat the boilers or something inside of houses, etc. We can use it to store the energy in electrical vehicles, and then we can use this energy from electrical vehicle when it's not being used, and things like that. This is the hub and spoke project. Is basically like making an artificial island which would be connected to 10 to 30 gigawatts of offshore wind farms, and then this island would be connected between several different countries, and the energy can be then switched from one country to another as the demand actually grows in different parts. And then so this is the classical one. We are just transferring electricity, or we can actually change the electricity to the hydrogen and then transfer the hydrogen to onshore, or we can actually do both. we can do both, or we can store the hydrogen offshore, which is this. This is a concept being developed by Technip, which is actually a oil and gas company. And so actually to retribute a little bit for all the oil problems that we have in CO2. So what they are planning to do is to have a wind farm that will be used to power their old rigs, and then they would store the hydrogen in the submarine tanks. And when the wind is not blowing, they need the electricity. We just use this hydrogen to produce the electricity. And the storing with the air, actually we put an air compartment on the seabed. And when there is no demand for the electricity, we actually, the surplus electricity, we just convert it to the pressurized air. We actually pump the air here under pressure. And when there is no wind, we can use this by actually releasing this, this air through the turbine and generating the electricity. And this way also we can control the peaks in the, in our supply. That's all. Thanks for attention. Do you have any questions?
Thank you. Thank you for thinking a long time. Questions? Ako želite, možemo na hrvatskom pitanja.
I have a question. So, are you perhaps familiar how the wind measurements are conducted? Because I imagine it's difficult because you need the entire high profile.
Every turbine has its own anemometer. So it's just like that. But actually, before, when the wind farm, if you want to develop a wind farm, you need to have measurements years before, actually. So basically what they do is, first you have measurements near shore, if you don't have offshore. And then after that, they actually build a met mast, it's called. It's an offshore structure that you actually install offshore. It's a big tower. And then, if you plan that your wind turbine will be on an 80-meter height, then you will try to put this tower to 80-meter height. You will have an anemometer on top, and then you will measure the speed there for 2-3 years, let's say, and then make models afterwards. Use this for planning.
Any questions?
Thank you very much.
Možda na hrvatskom zbog studenta, evo vidimo da je zapravo planiranje, projektiranje izgradnje ovakvih turbina zahtjeva, odnosno farmi, zahtjeva interdisciplinarni pristup. Dakle, suradnju građevinskih inženjera, geofizičara, inženjera tehnike, strojarstva i tako dalje. Možda da čisto razjasnite i zbog studenta koja je uloga građevinskih inženjera u ovakvim kompleksnim projektima. Sve te vrste oko energije, zapravo tu je konstrukcija nije toliko, nije fokus, ali isto tako važno.
Ja bih jedno pitanje jer je vezano, htjela sam pitati, Bekle je studirali građevinarstvo, ali i studij brodogradnje. Sad me zanima koja je vaša uloga, konkretno što vi radite, koji je vaš zadatak baš zbog ovog interdisciplinarnog pristupa.
Znači recimo, karijeru sam počeo kao projektni inženjer, znači na planiranju tih svega što ima sile operacije, što ima veze sa polaganjem i zakopavanjem kablova. I recimo građevinski inženjeri su svugdje praktički. U offshore-u tradicionalno su više bili strojarski inženjeri nego građevinski i oni su se bavili čak i građevinskim dijelom, ali građevinski inženjeri se poslove koje rade su praktički od geotehničkih istraživanja, od projektiranja ovih džeketa i svih ovih struktura što ste vi vidjeli, znači s obzirom na valove, utjecaj valova i morskih struja i tako dalje. Onda bave se isto recimo kablovima, stabilitetom kablova zbog utjecaja morskih struja i tako dalje, što je tu se isto bave dosta strojarskih inženjera tu. Bave se nadzorom gradnje, kao što sam ja bio isto po brodovima i tako po terenu na nadzoru. A trenutno radim kao konsultant i recimo trenutno sam radio na programiranju jedne aplikacije da bismo vidjeli koliko zapravo ćemo imati koliko ćemo izgubiti vremena zbog lošeg vremena zapravo u našim operacijama s obzirom na limite broda, visinu valova koji brod može izdržati i tako dalje. A ja sad trenutno polako idem u floating wind. I recimo ta brodogradnja je tu recimo jako zanimljiva gdje god ima bilo što je plutajuće, dođe super to znanje, a građevina onda za konstrukcije i što se tiče isto geotehničkog dijela. I isto neki građevinari također rade, prelaze ljudi, najviše idu ljudi geodeti, ali neki isto građevinari znaju preći u taj dio geodetski, pa rade geodetskom, batimetriju, snimanje batimetrije i tako dalje. I potencijala je jako puno. Mislim, stvarno jako je interdisciplinaran tim i interakcija postoji sa različitim specijalistima od svih faza, počevši od planiranja do izgradnje i poslije operation and maintenance. Da, tako je. Pa evo sad je isto, nedavno sam pričao sa jednim koji je cijeli svoj profesionalni vijek, praktički on je sad u penziji, mi se čini, proveo na projektiranju tih struktura, a sada se bavi više sa kablovima i procjenom gubitaka u kablu i tako dalje. Da, postoje ti prelezi, da. Što se tiče toga, u tim kompanijama je to puno fleksibilnije, recimo. I općenito nekako van je puno fleksibilnije. Znači, najprije se traži inženjera i onda inženjer mora biti fleksibilan, baviti se više različitih stvari. Hvala lijepo.
Evo mene zanima, koliko ste vi nakon završetka studija išli na nekakve druge edukacije, nekakva cjeloživotna učenja, nešto, ili se to bilo isključivo kroz praksu na vašem radnom mjestu, ili ste imali nešto negdje organizirano, za tvrtka imala organizirano?
Da, zapravo tvrtka nije baš imala organizirana, jer izvođači su dosta škrti po tom pitanju i jako rijetko plate šta. Ono što sam ja odradio je bilo nekakve safety trainings i takve stvari, sigurnost na moru i to, što je obavezno. Sada u ovoj firmi koja je konsultantska imamo više tih treninga u smislu sudjelovanja na nekim radionicama i takve stvari. A inače ja sam se sam obrazovao sve dodano što mi je trebalo, tako da sam istraživanjem na znanstvenim časopisima ili stručnim časopisima i od 2016. sam zapravo postao član kao graduate, sam se prijavio za taj Institute of Civil Engineers u Engleskoj i tamo postoji čisto taj proces koji je trajao godinama. Znači, ovlašteni inženjer sam tamo postao, položio sam tek u prvom mjesecu ove godine, tako da to je jedan proces koji jako puno zahtijeva vremena i edukacija dodatnih. Tako da to se čovjek mora sam educirati na način da si pripremi plan. Svako treba razmisliti koje su mu jake strane ili koje su mu slabe, onda na tim slabima raditi, napraviti plan u idućih godinu, dvije na čemu želim raditi i onda zapravo učiti na tome da tu pospješi. I to se treba evidentirati, naravno, jer se to gleda poslije prilikom prijave.
Pohrana energije s ovim komprimiranjem zraka, to u praksi već radi, koji su oblici?
To ne radi baš. Ovo je samo koncept od neke firme zapravo iz Malte, koji su sudjelovali u nekom europskom projektu, tako da mislim da to još nije izgrađeno. To je bilo
samo na osnovu environmentally unfriendly do ove akumulacije.
Da.
I also have a question.
Yes, please.
What are the natural frequencies of such towers? Do you have an idea?
Well, actually, really, on top of my mind, I think it's between. There is the frequency depends actually on the. It says this when the propellers go, so you have the frequency of one propeller and three propellers. Every time the propeller shades the tower, you get the loads, because actually your loading is reduced. So this is how you get the dynamics. And I think, and it depends on the loading. For example, the loading, I think, okay, the waves, the frequency of the waves is, between 0 something to 0.1 hertz. It's like up to 10 seconds, maximum 20 seconds periods. And then the wind can be, the wind is shorter, I believe. And the frequencies where you try to put this actually. So actually, basically what you look at chart of your loading frequencies of the loadings. You look at the chart of the frequency of operation of the wind turbine. And now the best thing to do is actually to put it somewhere in between. And this is, I think, between 1.2 to 3 hertz or something like that. I should check, but.
Okay, so you design it that way that all those loadings don't pose resonance.
Yeah, exactly.
Evo, ja imam pitanje, ovo mi sad baš ugodno iznenadilo da je jedan naš inženjer član komore britanske inženjera. Pa evo, rekli ste da je jako dugotrajan postupak. Kod nas, nažalost, moram reći, kod nas to ide vrlo brzo i to je nekakav nedostatak. Koji su zapravo uvjeti? Kako to, možda onako ukratko, to vjerojatno se može...
Da, ukratko uvjeti su, recimo, postoji taj dio, znači ako imate nekoga kao mentora, pa onda se ide initial professional development sa mentorom, to traje 2 do 4 godine i onda se napravi professional review report i onda se može pristupiti ispitu. A drugi dio je koji sam ja recimo uzeo, jer ja nisam imao nikog ovlaštenog u mojoj firmi, pa sam morao sve sam raditi. I onda ja sam zapravo išao na career appraisal, ja sam morao sastaviti jedan, recimo, rad sa svim svojim primjerima, recimo, na čemu sam radio i kako u tim primjerima dokazati da ja zapravo sam došao do nekih attributes što oni traže, a to je health and safety management, technical skills i tako dalje, ima 9, sad ih ima 7, malo su skratili. I kroz te primjere dokazati da imam to iskustvo. I onda ja to sam predao, oni su mi to rekli, ok, kao to ti je ok, iskustvo je ok, onda sam napravio offshore, professional review report, gdje se ja trebao opisati kroz 2 projekta kako sam sa svojim iskustvom, recimo, dobio te atribute, recimo, dokazati te atribute i onda se pristupi ispitu. I ispit je 15 minuta prezentacija, gdje vi jedan primjer od tog reporta zapravo ekspandirate. Onda imate 45 minuta do sat vremena usmeno ispitivanje i onda je sad i pol pisani dio koji nije težak, sad je to communication exercise, ali recimo taj usmeni dio oni moraju vidjeti da ste vi zapravo čovjek, to je najbitnije, kao da ste vi inženjer kojeg kada stave kad dođe na odgovornost, da neće napraviti nešto što može ugroziti ljudski život. To je najbitnije, znači da imate tu odgovornost i da koristite, da se bavite samo onim za što ste kompetentni i tako.
Izuzetno mi je drago da sam čula to iskustvo, jer naši se vrlo često pozivaju na britansku komoru koja ima veliku tradiciju, ali nažalost kod nas to ni približno nije ovako da bi se neko koji ima ovlaštenje imao sve te kompetencije.
Da, drugčiji je koncept.
Hvala.
Hvala. Nima još pitanje? Nemo. Evo, ja bih vam se isto zahvalila za sve izgledanje na festivalu i hvala za ovo. Hvala svima, sad je kratka pauza, u 2:15 idemo dalje. Morate si, iz mog iskustva nikad ne bude vremena onako da se posveti.
Mute.
Kako se ovaj?
Ma s ovim tu je glavno. Dole. Isključeno.
Mislim, dobro, ako ne radi ću sa strelicama. Nije problem.
Trebalo bi raditi, ne znam. I sad.
Ok. Super. Ovo je. Ok.
Tu je. Tu smo. Samo da upalim snimanje još.
Ok. Hvala. Nisam sigurna da li na hrvatskom, da li na engleskom, pola na hrvatskom, pola na engleskom imamo.
Ma na engleskom.
Okay. Igore, just molim te ti. Okay, so we can start with the third lecture. Our third lecture is Valentina Kocijan. She graduated at the Faculty of Mining, Petroleum and Geology in Zagreb. And after her studies, she had specialization in Madrid and Paris. At this moment, she is working as engineering geologist employed in GeoTech, and she's also a PhD student at our postgraduate study program. So she will give us a lecture, Slopes of Higher Protection Priority Rating using Modified Colorado Rockfall Hazard Rating System.
Hello everyone, as Professor Sanja already said, my name is Valentina. Today I'm going to tell you a little bit more about rock mass classification called Modified Colorado Rockfall Hazard Rating System. We use this rock mass classification on one of our projects in the company in 2018. And it is really special classification because it's taking into account a lot of factors that are not usually used in normal classifications. So here's the content of my presentation. In introduction, I'm going to introduce to you a project. Then I'm going to tell you a little bit more about engineering geological mapping and why is it important in civil engineering. I'll introduce to you geological features of the studied area and tell you more about Modified Colorado Rockfall Hazard Rating System. I'll introduce to you results and then I will conclude the presentation. So the study road section is located on southeastern part of Istrian Peninsula. It's connecting villages Brseć and Mošćenička Draga. It is approximately 8 kilometers in length and it's very windy, very curvy. It was executed by cutting into the existing terrain, and that opened subvertical slopes up to 16 meters in height. During the past years, there were often rockfall events. Rockfall is the fastest and the most common type of landslide, and it poses threats to infrastructure that is positioned under the rock slopes. Investor gave us the request, since it's a very large-scale road. They gave us the request that we have to single out the sections that needs to be remediated first. So we decided to use Modified Colorado Rockfall Hazard Rating System because it's specialized to do exactly that. Firstly, I'm going to introduce to you engineering geological mapping and why is it important. Engineering geological mapping is recording of geological information from rock outcrops on the field. We gather information like geometry of the rock slope, we identify rock type, discontinuities, and their condition. And with this information, we evaluate the stability of the rock slope. The stability of the rock slope is actually defined by the strength of discontinuity and the intact rock. But also what influences the stability is actually the number, orientation, distribution, and state of the discontinuities. This is important because we have different types of failures that can happen when you're either doing the remediation or cutting into the existing terrain. So we have to identify them. We have main three types, which are plain, wedge, and toppling. We also have a combination, but that's something else. Plain type of failure is predisposed by the pre-existing bedding plane. It can be either bedding or other type of discontinuity, but it is in the same orientation as the slope orientation. So here is the graphic interpretation of the plane failure. It is going in the same direction as the slope. The wedge failure is predisposed by two intersecting discontinuities that create a wedge. In this case, it's also going in direction of the slope. So it's planar wedge failure. It can also go in the opposite direction. So that would create toppling wedge failure. And then we have the third type of failure, which is toppling. It is also predisposed of some kind of discontinuity, but is in the opposite direction than the orientation of the slope. Here are also stereographic representation of discontinuities in relation to the slope orientation, where we can read out, after we measure the orientation of discontinuity, we put it on a stereographic mesh, and then we can read out what kind of failure it is going to happen in that rock outcrop. On the next slide, I have put three pictures that represent the three types of slopes. Here we have a plane failure, wedge failure, and toppling. So why is engineering geological mapping important? It is important because it is the first step when we have some kind of geotechnical problem. We first go to the field and we have to do outcrop stability assessment. We use one of the given classification. It is either GSI, RMR, SMR, Q classification, Colorado classification. We have to choose a type of rock mass classification that is suitable for the type of the project that it needs to be carried out. Because the information we gather with rock mass classifications, civil engineers use it as the input data for geotechnical design and then to predict protection measures for the rock outcrop. Shortly about geological features of the area. As I said, the road is positioned on the Istrian Peninsula, and it is part of Učka-Čičarija only. And if you speak to the locals, you will hear that this is part of White Istria because it's built out of limestone and dolomite, which are white in color. And it is a tectonically very active area. It was in the past, geological past, but also today. And this results with many discontinuity systems and fault zones, which result in different structural problems within road cuts. The other factor that contributes to that is the curviness of the road, which cuts the orientation of discontinuities in different ways, and that creates different kind of failures. A little bit about classification. Rockfall hazard rating system was developed in early 80s in the state of Oregon in US, but as the infrastructure grew and the frequency of the traffic increased, they had to modify it to current state, and that was done by Russell in 2008. It is used on large scale road sections when they need to define Rockfall project priorities and allocate the limited funds. Factors that contribute to the rockfall according to this classification are slope profile factor, geological factor, climate, presence of water and slope, which gives us total hazard score, and also rockfall history, number of traffic accidents attributed to a rockfall, that gives us total risk score. And if you compare both of those factors, you have the result of which sections you need to prioritize when you have to remediate the slopes. Here I listed geological factors. They are degree of undercutting, jar slate, weathering degree of rock mass, block size or volume of material expected to fail, number of discontinuity sets, resistance orientation, aperture, weathering condition, and friction of discontinuities. I think that most of them are clear what it means. If something is unclear, you can ask me afterwards. I would say that this classification is a lot simpler than the standard classifications we use. In comparison to, for example, RMR, which is widespread in this part of Europe, let's say. In RMR, you take most of those, you give some or take some. It doesn't matter, but you have to take each discontinuity set and to describe each discontinuity set, and another one, and another one, and another one. And it's quite time consuming. And if you have one rock slope, rock outcrop, it's pretty useful. But if you have 8 kilometers, it's time consuming and, let's say, unnecessary. This classification is simplified because it has only 4 levels of scoring, and you take whole section and you score the whole section. So it's faster, but it also takes into account other factors like climate, like traffic conditions, the slope profile condition, rockfall condition, and etc. Here are slope profile factors. It's slope height, slope inclination, slope continuity, ditch catchment, and segment length. First, I'll explain this picture. Here is the example of the slope with minor launching features. It means that the topography of the slope is not as developed, maybe, and it's the 3rd grade. So first one is none, then it's something, then it's minor, then it's major. So it's the 3rd grade. We have high undercutting degree, 3 discontinuity sets plus random discontinuities, and type 4 ditch catchment, means that it doesn't have any barriers present. And here I have a picture of slope with many launching feature presence, medium undercutting degree, 3 discontinuity sets plus random discontinuities, and type 2 ditch catchment, which is effective hexagonal mesh. I just wanted to give those examples just to show you how easy it is to score the slopes with this. You have only few things you have to take into account, and you're quickly done. Then we have climate and presence of water on the slope, which takes into account annual precipitation, occurrence of freezing thaw periods, seepage or water present on the slope, and slope aspect. Slope aspect means to which direction of the world is the slope orientated. Precipitation amounts can be found on web pages of meteorological stations. In each state, you have annual, monthly, even for decades, the base for that. There's also rockfall history. It is a frequency of rockfall occurrence. There are unfortunately not no official data for Croatia, and to get those information, we had to talk to locals, to road maintenance, to search the articles in newspapers when something happened and something. And the last factor, we have traffic conditions. We have their side distance, average vehicle risk, and number of accidents caused by rockfall. Let's say side distance here is very important because it also takes into account the posted speed limit. According to the posted speed limit, we can calculate how far you can see, what is your angle of viewing when you're driving. So this is very interesting, actually. According to the number of given points for each zone, actually we categorize the zones to overall hazard categories and overall risk categories. Overall hazard categories have low, medium, and high, and overall risk categories have low and high. And if you compare overall risk to overall hazard, you get three groups that are A, B, and C. Then A, let's say, is the one that it's not necessary to fast remediate, and the C is urgent remediation measures. So finally, results. On the road of 6 kilometers, we singled out 66 different zones with lengths from 20 to 300 meters. And we defined those zones during engineering geological mapping. We grouped them according to similar slope characteristics. And also as a background to this classification, since it was new and we didn't actually know how it's going to be applicable to our civil engineers, we backed that up with the discontinuity set orientation measures, and we defined structural failures that are possible. So they also had those additional informations. And we highlighted the individual rock blocks that are unstable if they were present. So number of given points for overall hazard ranges from 0 to 1068 and from 0 to 165 for overall risk, where higher number represents higher priority slope protection zone. 13 zones are categorized to the group A, 16 zones are categorized to the group B, and 37 zones are categorized to the group C. And from that, we can see that most of them are categorized to group C, and that is actually a confirmation of the really geological complex wide area that poses significant rockfall hazard. Here on the picture, we can see the distribution of one part of the road. The red line represents the group C, which is immediate remediation measures. Yellow line is the group B, and green line is the group A. According to the recommendation on the study road section, different slope protection measures were carried out. We had underpinning with stone blocks, installation of galvanized double-twisted hexagonal wire mesh with or without steel ropes, installation of rod and self-drilling anchors, installation of shotcrete, profiling of rock slopes, installation of New Jersey bumpers, and removal of potentially unstable blocks. Here are 4 pictures of slope protection measures that were carried out. I couldn't take a photo of all the measures because there are not a lot of auto stops along the road. Here on the first 2 pictures, we have double twisted hex wire mesh, and on the other one, other 2, we have hex mesh with steel ropes and self-drilling anchors. And as a conclusion, this is very interesting rock mass classification. It is simplified according to the geological aspect. It can be done faster, but it also takes into account the climate factor, the traffic factor, and rockfall history. And it's useful for large-scale road sections. It would be very useful to further develop sedimentary rock mass classification, including flysch rock mass as a separate one, since in Croatia, most of the coastal area is built out of carbonate rock or flysch rock mass. If to do that, we would have to also standardize the classification to metric system, and also to the seasonal traffic frequency, since the frequency of the traffic in Croatia is a lot higher in summer, and also to climate features, since in US they have freeze and thaw periods, and here, for example, we don't have that. Unfortunately, until this point, there is no systematic mapping of road outflow present. We only go on field when rockfall occurs and there is funding available. And this would be very, let's say, useful to do this, because geological complexity of wide area poses significant rockfall hazard. And systematic mapping with this classification would give us an overview of potential hazardous sections over the country. So if we would do it systematically, it would minimize the rockfall problems that are happening during, for example, large precipitation periods. And that's it. Thank you for your attention.
you. Okay, now we can start with the questions. Možda je na hrvatskom, ako...
I know.
Start, what do you think is the main disadvantage of this classification?
The main disadvantage, in my opinion, is that they don't have the correction of points for the orientation of discontinuities. That's why we backed up the classification with additional measuring.
You have to check it in the second step.
Actually, we didn't check it. The classification doesn't have the measuring of discontinuities. They have this part where is that is taking into account how diverse the topography is or what is the level of undercutting, but it doesn't take into account the direction of discontinuities itself. It doesn't give us the information if it's going to be a wedge or planar or toppling.
If we did this in a systematic way for the whole country, I think this might be a great disadvantage because we could rate something as hazardous or risky, but you have to check. I think it would be useful to check in the second step what's the orientation of the.
I agree, but also if we would do this systematically, we can also, if we are going to standardize this classification for Croatia, we can add another step into the classification.
Okay.
So, do you have enough funding for all of the measurements that you suggested? Because you said at the beginning that the stretch of the road was 8 kilometers and the actions should be taken on top of this line.
Yes, we had the investor Hrvatske ceste that gave us funding to do it this way. Since there were a lot of rockfalls present during the years, it was, let's say, burning under their feet. So they had to firstly implement protection measures to the slopes that are of high risk, and then to the ones that doesn't pose that great of the risk.
So if you would have smaller funds available, your suggestions would scale up accordingly?
If we had, for example, smaller funds and smaller rock slope, we wouldn't use this. We wouldn't use this classification, because if we have a slope of 200 meters, we can do easily RMR classification or something that is more extensive, but on a smaller scale, because we don't need to take into account the traffic condition there or a sight distance, because it's small. Yeah, local.
What would be the possible implementation of 3D mobile scanning data, since those data today are more and more cheaper? For example, Hrvatska outlet says they make a lot of this measurement. I don't know if Hrvatska says that. So what might the application of those?
I think it would be good if that kind of data would be available, because as I said, this classification doesn't include measurements of discontinuities. Even though these days Professor Arbanas and her team of students, they're already having automatically measuring of the discontinuity systems. So that could also be implemented. But if we have 3D point clouds, we can easily see what is the degree of undercutting, what is the slope profile. We can measure what is the height of the slope. So it could be done more elegantly, let's say, with this data.
What this method provides or not?
provide.
So your application of point problem.
No.
Okay. So this can be developed or something?
Yes, that would have to be developed.
Okay, what data did you use for your analysis? Only terrain investigation or some data that were existing, some maps or?
Yeah, we were using geoportal maps, which means orthophoto, Croatian base map, topographic map, also geological base map, meteo station data, data about rockfalls that we had to research, and the rest was from the field.
Okay, other questions? Thank you, Valentina. Okay, the lecture Why Rainfalls and Earthquakes Trigger Landslides will be given in the name of group of authors: Martina Vivoda Prodan, Josip Peranić, Nina Čeksa, Željko Arbanas, Sara Palić by Sara Palić. I will just read some words about Sara Palić. She graduated from the Faculty of Civil Engineering, University of Rijeka, obtaining a master's degree in 2016. She has enrolled in the postgraduate doctoral study program in 2017. From May 2019, she's employed as a research assistant on the project Physical Modeling of Landslide Remediation Construction Behavior under Static and Seismic Actions, funded by the Croatian Science Foundation. Her PhD research is focused on the use of similarity laws in modeling small-scale landslide physical models. She was teaching assistant in several undergraduate and graduate courses.
Sanja?
Okay, hello everyone. Sanja already introduced me. My name is Sara, and today I will talk about landslides as a phenomena and their most common triggers, rainfall and earthquakes. I will tell you a little bit about the project that my team is performing at the moment and how it connects to the landslides and their most common triggers. So there are many known natural hazards. Among them are earthquakes, floods, landslides, volcanoes, and so on. Just a few are mentioned here. We will focus today only on landslides, but later you will see that other natural hazards like earthquakes and floods can cause also landslides. Any slope movements are classified by Barnes into two different terms: type of movement and the material type. Type of movement can be different from falls, topples, slides, spreads, and flows, and the material type can be divided into rock and engineering soil, that is soil and debris. Depending on the combination of the type of movement and the material type, we can characterize different variety of landslide types, and you can see some of them here in the videos. Let me just see. Okay. What is actually a landslide? Landslide is considered any movement down the slope of a mass of rock, debris, or earth. Landslides usually occur when shear stresses acting on a slope exceed shear strength of the slope itself or the material forming the slope, or that is the resistance to shearing of the material. These two videos just to see what kind of landslides exist or occurred around the world. This one here in Norway actually occurred because of the characteristics of the material itself, and the whole sliding plane went into the sea along with some of the houses. There are many triggers of landslides, from snow melting, heavy and recurrent rainfall, to earthquakes, even avalanches and other triggers, but we divide major causes into geology, geomorphology, and human activity. Geology refers to the characteristics of the material itself. We can have earth or rock with weak and fractured layers. We can have different, as you can see in this photo, different layers of different strength, different stiffness, different permeability, when in combination with hydrology, with rainfall, can cause landslides. Geomorphology refers to the structure of the land itself. For example, those slopes that are not covered in vegetation due to fires or droughts are more prone to sliding. Why? Because a system of roots of trees, plants, and bushes holds the soil together. So they're not covered by vegetation, are more susceptible to sliding. And of course, maybe the main cause in this modern time is human activity. Due to a large in population growth, a lot of slides happen because of agriculture, construction, illegal slope cutting, mining, and so on. On these two right pictures, you can see landslides that happen due to mining related. If you look at this figure, we can see a period from 1903 to 2019, where all the occurred mass movements are registered. Here we have not only landslides, but also avalanches, subsidence, and other movements of the slope, but we can establish that there is an increase in the number of mass movements throughout the years. Although most of the landslides don't happen in a populated area, a large number of landslides occurs in extremely populated area and affects millions of people, causes hundreds and thousands of injuries and death each year. Of course, there is a huge economical effect annually, millions to billions of dollars of damage. Also, for the same time period, we can see that the trend for number of injuries and that is also growing, so it's also increasing. Same for the economic damage globally. This is for the period from 1950s to 2019. Again, growing economic damages. Before introducing the project and what our team does, I would like to present some of the worst landslides that happened worldwide throughout history. One very old landslide, but very interesting to mention, is the one triggered by, or not landslide, but landslides triggered by maybe the world's deadliest earthquake of the 20th century, the Haiyuan landslides in China in 1920s. More than 50,000 landslides were activated. Almost 700 of them were characterized as major landslides. It had such an effect that some of the rivers changed its course, some rivers were dammed, a lot of people, around 200,000 people died from the landslides and from the earthquake itself. Another very interesting landslide, one of the largest debris flows in history, is the Vargas debris flow from 1991 in Venezuela. It started after several days of torrential rain, which caused flash floods and debris flows all around the coastal zone in Vargas. over 1.8 million tons of freshly deposited sediment was spread during the floods. You can see on the picture how much of the coastal area was damaged. Then we have the La Conchita landslide. The landslide on the photo on the right is the initial landslide, the original landslide from 1995, which didn't cause any injuries, any casualties. It moved very slowly and people were able to evacuate. But the landslide that happened 10 years after happened after 15-day period of a record amount of rainfall, and this landslide moved very rapidly, so there were some casualties. Unfortunately, even though the landslide was studied by scientists, this movement was not predicted. One bit older, but closer to us, in Italy, the Vajont Dam landslide in 1963. After the dam was built, the dam was filled, and during initial filling, landslide from the Monte Toc, it was around 260 million cubic meters of rock material that went into the lake of the dam and caused, you can see on the video in the beginning, two waves that formed and went to opposite parts, one down the dam and the other on the other side towards the village of Etro. The village was protected by the mountain, but a mega tsunami was formed and overtopped the dam and went down to the valley, destroyed completely the village of Longarone. Interesting, there was no bigger amount of damage to the dam itself. And the last example, the one closest to us from 2018, the Hrvatska Kostajnica landslide. There was no casualties reported, damage only to a few houses, but it's of course one of our own here in Croatia, so for us it's very important. The slope failure occurred as a combination of many factors, from geology and rapid changes of temperature from below to above zero in a short period of time, which caused the snow melting. Approximately 80 centimeters of snow melted, and of course Una River flooding, which was close to the Hrvatska Kostajnica, and a period of rain. Those combination of factors triggered the large landslide. To get back to our triggers, the most common triggers among a lot of existing ones are earthquakes and rainfalls, and this will be the focus also of the rest of the presentation and also of our project. We can see in this figure the global anomaly of precipitation. So from the average, we can see that most of the points in the last 50, 60 years go over the average line, are positive values, which means we have much wetter and greater than average annual precipitation, while in the beginning of this we have negative or drier values. Well, why is that so? We can attribute this to climate change. Earth's surface is warming up. There is a lot more evaporation, and of course, because more water goes into the atmosphere, more precipitation occurs. So, of course, there is more precipitation than before. We also have, if you look at the figure with the number of significant earthquakes, we have a growth in the number of significant earthquakes. This can also has to taken into account with some, it should be noted that this first period is much less likely to contain complete data than the data contained in the last few years. So these two effects, increase in the significant earthquake events and trends of higher than average precipitation all around the world, with a combination of growing of the population needs, urbanization of all areas, construction, infrastructure development, and so on, leads us to the increasing number of slope failures. So more and more landslides. The risk of landslides is not reducing, the danger is getting bigger because of all these elements here. One of the means of reducing the risk and dangers of landslides are landslide remediations. Remediation measures have the aim to reduce the active forces acting on the slope and to increase the resistance of the soil at the slip surface of the slope, or to combine them. On the figure below, we can see almost all the possible remediation measures that are used in the geotechnical engineering field, from drainage, installation of drainage and geogrids, to retaining walls or bolts, to using vegetation as means of stabilization, or friction piles. So everything in one picture. And now we get to the idea of our project, the idea of physical modeling of landslides. Why use physical models to investigate landslides? They enable us to investigate and they enable us new knowledge in the field of soil material of landslides and remedial constructions that cannot be achieved in real size landslides. So it's not possible to predict remediation for all kinds of materials, places, and all kinds of landslides. By using large or small scale physical models, that gives us the ability to observe hydraulic and mechanical response of soil slopes under conditions, initial and boundary conditions that can be controlled completely by the one doing the experiments. On these pictures here, on the right, you can see landslide Zgrade near the city of Pazin. You can see in the middle the remediation of the landslide, and you can see a part of our physical model and the same or similar remediation done in our experiment. This is just our project, name of our project, funded by the Croatian Science Foundation, members of our research team, our website. The main idea, the main object of the project is to analyze and model behavior of landslide remedial constructions, of scale landslides under static and seismic conditions. That is the major triggers that we mentioned before: rainfall and earthquakes. Since we have two major triggers, we have two different physical models, one in static and the other is in dynamic conditions. The first model is a bit bigger. I will say later why the dynamic is smaller. It consists of steel elements on a working table and transparent plexiglass walls, which allow us to monitor the infiltration of the water in the slope. Model is 0.5 meter in height, the height of the plexiglass walls. So the maximum depth of the soil in regard to that can be only 30 centimeters. Slope inclination can be adjustable from 20 to 45 degrees. And later I will show you two tests at slope inclination of 35 degrees with and without remediation measures. Static conditions or simulated rainfall are induced by using a rainfall simulator or from sprinkler simulator from 3 nozzles. We have three branches of sprinklers, one in each part of the slope, lower, middle, and upper part. And on this diagram here, you can see the changes of the rainfall intensities. Depending on the type of material that we use, slopes can be exposed to different rainfall intensities. So it can be adjusted depending on what kind of material we want to experiment on. The other model, the smaller one, is for dynamic conditions. Its elements are made of aluminum to make it more light, again with the transparent plexiglass side walls. It is now 0.5 meter wide and 1 meter in height. Again, we have a maximum depth of the soil material from 10 to 15 centimeters, this time due to the limitations of the shaking table that provides the dynamic excitation. Earthquake is simulated by a shaking platform, a dynamic excitation. We have uniform seismic excitation of sinusoidal shape. As rainfall intensities could be adjusted in the static conditions, here we can adjust amplitude and frequency. So this is the shaking table. Our model is our model lies on, mostly because of the limitations of the model. This is much smaller than the static one. Here we have the monitoring equipment. Two systems exist, geotechnical monitoring system and geodetic monitoring system. Geotechnical monitoring system is consisted of soil water content sensors, mini tensiometers, pore pressure transducers to be able to measure water moisture content, positive and negative pore pressures, accelerometers for measurements of acceleration, velocity, rotation of the material. And here on this picture on the right, you can see the installation schematics of our water-related sensors. We can see that there are different profiles, 3 profiles, one for each part of the slope, where our water-related sensors are installed, and they are installed at different depths to be able to get the complete picture, to observe complete picture of temporal spatial evolution of different variables we are measuring during the experiment. And this is how those results of the diagrams of the measuring look like. This is just for the example for the depth of 6 and 18 centimeters. The geodetic monitoring system is consisted of two pairs of high-speed stereo cameras, a terrestrial laser scanner, and a digital camera for structure from motion photogrammetry surveys. The cameras, both pairs of cameras are shown here, and these are example results from which can be obtained from those kinds of cameras. We can monitor surface displacements. The camera recognizes a point and can monitor it during the whole experiment. Of course, after the sliding of the surface, some of the points will be lost in the measurements. On the right side, we have the TLS terrestrial laser scanner and results obtained from the 3D point cloud of the scanner. This is for the model before starting of the test. And getting back to the landslides and the complexity of landslides, there are a lot of elements that must be satisfied in when trying to compare physical models and real-life landslides. You can see all of those elements here in these circles. We have elements regarding geometric, dynamic, and kinematic similarity. All those arrows mean that all of those elements are interdependent. So each element depends on many different similarities and many different elements. It's a very complex process. So if it is not possible to obtain all the elements of similarity and to satisfy them to achieve a perfect physical model to describe a real-life landslide. Even though the perfection of the physical model is not possible, it gives us a lot of valuable data to be able to investigate the mechanisms, the different mechanisms and processes of landslides from initiation, runoff, and the failure itself. Now I'll show you the two videos from two different models, the static model with a simulated rainfall and the dynamic model. So this is the basic model with the basic material, the sandy slope. As rainfall falls onto the slope of the model, rainfall is infiltrated into the model, and we have a formation of the groundwater table at the lower part of the slope. The groundwater table reaches the surface and the toe of the slope, and there we can monitor in the beginning of the video the formation of the first cracks and the first failure. After that, the landslide slip surface develops retrogressively to the top of the slope, which is shown in the end of the video, and then it stops when there is no more material to slide. And the other model, where our slope is induced by the shaking table. Here we have a different type of failure. We have a failure at the top of the slope. Of course, we can adjust here different frequencies and amplitudes to initiate the slope failure, of course, limited a lot by the size of the model. So this failure was a bit harder to obtain. And for remediation measures, or the comparison of the remediation measures, this is the small scale model of a sandy slope at 35 degrees inclination with and without remediation measures under same rainfall intensities. The remediation measures were gravity retaining walls that were 3D printed. And again, pictures from the same slope model that I already showed you in the video. This is when the failure already occurred, and now it retrogressively develops to the top of the slope. This is the last one. And when looking at the remediation measures, or the other model with the gravity retaining wall, this is before the start of the test, and this is at the end of the test. You can see that there are no cracks at the slope. Only after the rainfall was intensified in the upper part of the slope, there was too much water to infiltrate the model. The process of erosion started and a debris flow was initiated. This is the look of the gravity retaining wall after the experiment, and this is a short video of the debris flow. So no cracks in this part of the slope. Of course, the material behind the wall was replaced, sand was replaced by gravel. And here we can look at the 3D survey of the terrestrial laser scanner. What we can notice is, looking from the sides, that the wall did have a bit of a horizontal deformation during the experiment, specifically after the debris flow was initiated. And we can see this in 3D. So to conclude, I would like to say that this is just a part of the research of our team, of our project. Landslide is a very complex process, and a lot of different fields and areas in this process can be investigated. These physical models can be used with a variety of initial settings, conditions, different materials, different remediation measures, as you've seen before, not just gravity retaining walls, but also pile walls, gabion walls, etc. So this process, this research can continue many more years after our project ends. So it's a very, very wide field. That's it from me. Thank you.
Sarah, okay, we can start questions.
So, how do you choose the type of the material that you put inside this slides?
For the basic tests, we started with sand because it's the simplest material possible. It has relatively simple behavior of infiltration of rainfall into the slope. The behavior is maybe best known to us, and also those kinds of tests are done in 2 or 3 hours. We did tests, I think there is 12 or 13 tests altogether. Some were done on the basic sandy slope material, and others were done with a percentage of kaolin clay, 10% and 15%, to monitor different kinds of materials. They represent clay, although they are not completely clay materials. These type of experiments last longer. If we went to completely clay materials, it would last for weeks or maybe months even. So we started with the basic one, and this is the one that whose behavior is easiest to monitor.
Other questions? How about the smaller model figured by shaking? How long was this testing?
Testing was very, very short because we are limited by the number of, as cameras have their frames per second, the number of frames the cameras can record. So after the recording, if anything happens, we are in trouble because we didn't film it. So we would induce, I don't know, some kind of amplitude. We would go up, or I don't know, put a constant frequency and increase the amplitude, or the other way around. And when the camera stopped filming, we stopped the tests, and so on and so on. But it's for shaking table tests, it's a very small model. It's hard to obtain failure with this amount of mass of soil. Usually those kind of tests are done with much larger shaking tables. We were not aware of that at the beginning of the project. We had a lot of trouble when we started this. And also a lot more water should go into the model when performing dynamic experiments, and we don't have, it's hard to combine water and shaking table. That's the biggest problem.
No. Okay, thank you, Sarah. Ja bih si dala za ove predavanje i za autore koji nisu ovdje, i također bih iskoristila priliku da pozovem našu kolegicu Martinu Vivodu Prodan, koja je isto autorica ove prezentacije, ali da primi zahvalnicu za cijelu hrvatsku grupu za klizišta i na račun organizacije izložbe. Sad je jučer otvorena, možete ju pogledati na Kocijan. Ok, sad imamo opet kratku pauzu, pa možete se malo osvježiti 15 minuta, pa se vraćamo.
Ja ću gore još uključiti ovo snimanje. Samo ćemo probati malo pointer još. Da li hvata. Da, dobro. Uključiti.
Ok, evo, hvala se, ali publika se umorila. Okay, let us welcome our next lecturer, Jan Tomec. He will give us a lecture, Real-Life Applications of Beam Modeling. Jan Tomec is a PhD student from Slovenia, working as an early stage researcher at the Faculty of Civil Engineering in Rijeka. PhD study is supported by the EU project Joint Training on Numerical Modeling of Highly Flexible Structures for Industrial Application. His research title is Stable Long-Term Numerical Integration of the Kocijan rod problem in large overall motions. Please, Jan.
Thank you for the kind introduction. So, with the general public in mind here, I will try to focus today more on practical applications of my research, since it's heavily motivated by the industrial applications. So I'm part of the THREAD project, as I mentioned. So this is a European financed project. Its topic is numerical modeling of highly flexible structures. This includes 11 universities and one non-academic partner, basically a company. There's 14 positions filled by young researchers and 14 industrial partners. So each researcher has so each project is motivated by an explicit industrial application in mind. Yeah, so we are really coming from all over the world. So these European projects are always trying to promote internationality. So, for example, I couldn't apply in Slovenia for this project. I had to go abroad, so I chose Croatia. Yeah, and we have other students from the USA, for example, and from India and Pakistan, wherever. So, yeah, we are working tightly with the industry. We are really going a lot on different events where we have trainings. These include theoretical lectures, but also practical engineering stuff. For example, company tours and so on. So yeah, we're usually so. Everyone's project is a little different, but usually our projects are 3 years long, and then we have a few months of a secondment in some industrial partner. For example, I went to Ljubljana to Space SI, which is I will tell more about it later. The main focus of our projects are beams. So these are structural elements. I mean, they can represent basically anything, but theoretically they describe long thin objects. So we have some sort of line which is traveling through the center of the object, and then we have cross section which is perpendicular to it and describes then the entire volume. And we try to describe all our structures with this kind of theory. What we need to, so to have the full description of our body, we basically need the position of this line and then also the orientation of the cross section. Since it can be perpendicular, it can also tilt a little if you have some stress inside. now let's start with the industrial applications of where can we use this theory. So I will start with the first example, which is manufacturing yarns and ropes. This process, this process is really long. We know it from antiquity. We have fibers, which are, or strands, which are then twisted around each other to form a rope, and then you can also use these smaller ropes to make larger ropes and so on. So just twist them around each other, which makes them stronger and so on. This is an application that is the advanced application of the same process, but today. So what are we looking at is basically we have steel wires instead of I don't know, cotton fibers or so, and they're no longer making a rope. They're making some sort of like elongated structure, and you have instead of 3 simple yarns, you have I think it's 250 of these wires all twisting together and so on. So it's really complicated process. And this is an example from a Belgian company, Syntex-Bell. And so you can imagine you can also switch these wires and use, instead of steel, for example, you can use carbon fiber and stuff like that. So you can have really complicated braiding, which results in new shapes. But at the end, to be able to produce stuff like that, you need to be able to model it. It's no longer as simple as before. So you no longer have 3 strands, you just twist them together. You have lots of motion going on. You have to be able to simulate that motion of the strands themselves, but then you also need to be able to take into account the bending of these wires and so on. So it's really a complicated process. This is some of the simulations that are going into their research. So here is actually my simulation of twisting 2 wires, but you can imagine you can extend that to n number of wires. Here are some of their simulations of really complicated. So you have twisting around the fibers, and then you have fibers, so they form strands, and then you have strands twisting around each other to form rope and so on. Yeah, this is really one interesting application of the beam theory that I explained, that I quickly explained before. The next one is coming from the automotive industry. So we are looking at the assembly line, which was first invented by Henry Ford in, I think, around 100 years ago. So basically you have this assembly of the entire car, which can be divided or split into smaller jobs. You then move half-assembled cars from one station to another. The workers are specialized in their own jobs. They do it much more efficiently because they only need to learn a few skills to be able to do it, instead of having to know how to assemble the entire car, and also don't need to look around for the tools and so on. So it really amplifies the efficiency. So you got from a series of few hundred cars to millions of cars. Yeah, this is next evolutionary step. So basically you change the manual laborer with a robot. Still the idea is the same, but now the repetitive tasks are really taken on by robots, which can do everything faster. They can they're not concerned, they're not tired, they're not concerned with health and so on. So the problem is that nowadays, actually, most of the stuff that can be automated has already been automated. So there are still some processes which can be, for example, when you have when you're laying out wire harnesses in cars, you have hundreds of cables which actually still need to be put there by hand, and yeah, those kinds of processes are still not able to be automated. But there's a new new generation of robots which are no longer focused on replacing the worker, but now try to focus on aiding the worker, so to help them do the work efficiently, or perhaps it wouldn't be even possible. For example, if you have some extreme environment, maybe underwater, maybe a really hot environment and so on, or maybe you have, I don't know, let's say very delicate pieces that need to be precisely moved together, or maybe you're trying to lift a car, whatever, a robot can help. So you basically still need to give it some instructions, but it is able to do some tasks autonomously. Here is an example from Belgium, University of Liège. It's a robot trying to pick up an apple. So it seems like a trivial problem, but it's really hard for a robot to do stuff like that. So this robot is being thought of how to pick up an object that is of general shape. It's a little bit unpredictable. For example, you can replace the apple with a coffee mug, or I don't know, let's say potato chips, whatever. And it should still be able to pick it up. So the problem is that robots are usually programmed to do tasks precisely. For example, the machines that I showed you before, they were welding cars, but the process itself is really complicated, but you have the always exact same configuration. So the car stops at exactly the same spot, the welds are always in exactly the same position, so on. Here, the shape of the apple is no longer exact. So you have, of course, different kinds of apples, but also you have, so you're also trying to pick up anything that is around the same size. So you really need to have a different approach to it. What they're doing is they're using machine learning. So you're probably familiar with it, but nevertheless, for example, if you're trying to apply machine learning to recognize images, you can, for example, feed it. So the process is called training. So you basically feed the algorithm, I don't know, let's say 1,000 photos of cats, and then it's able to distinguish a picture with a cat or without it. But to do that, you first need data. So in this case, you need pictures where you know if there's a cat on it or not. In our example, what you need to do is to have experiments where the robot is trying to lift the object. So, for example, the robot is trying to lift the apple. If it falls, then it's unsuccessful. If it stays in the arm, then it's successful. But of course, if you would, so for this machine learning technique, you need a lot of examples. So for example, if you had 1 million of experiments and you would try to, if optimistically every experiment would last 5 seconds, which is really impossible, then it would altogether take 58 days. So this is really not an option. So you need to be able to do it virtually. So what they're doing is basically they're making a digital model of the robot, and then they are trying to lift the apple virtually on the computer, basically, and they can then make all of these million experiments in a matter of minutes. Yeah, this is basically a robot model. So here they tried 2 different approaches. One was to use the first approach is obviously the simplest one. They tried to use stiff or rigid arms instead of so this robot, maybe I can go a few slides back. So it's basically made of 2 arms and then some tool at the end. So they tried to model the thing with as if these arms were rigid, which they look like they are because they're really thick and so on. But at the end, they figure out that the models, after they tried to do some initial testing, resulted in a lot of vibrations and so on, which is really not the case in the physical environment. So they needed to update the model, make it a little more detailed. So they tried to do tried to model these arms, which are previously rigid, as flexible. So we arrived back to the beam theory, which I was talking at the beginning. So they were using they used the beam theory, and they were able to really capture the reality behind this robot. And with it, they were able to do those millions of experiments that I was talking before. Here is a small animation of how you can apply some motion to beams and make estimations of how it's supposed to move compared to the initial boundary conditions. So the last application that I will talk about is space application, which is the area which Space SI is dealing with. So as I said before, this is directly connected to my project because they're our industrial partner. So they're developing satellites, and this is a picture of a rocket. You see, most of the rocket is made of these three stages, which are rocket motors or rocket stages, and most of each stage is really just a container for gas and for air, for fuel and for air, which then combines in the engine and goes through the nozzle as really hot exhaust. And you have multiple stages because you have when you're gaining altitude, so you have different atmospheric conditions, and also it's more efficient. So for example, you don't need to carry this extra weight if you drop it and so on. So you basically burn the first stage, you drop it, you burn the next one, drop it, and so on. At the end is there a really small part with the actual load of that the rocket is trying to lift into the space. So this is usually a satellite. It can also be, I don't know, a nuclear warhead, or maybe people if they're going to the International Space Station. So on the actual mission that took place to carry up the satellite that I was working on was actually, I think, the first application of this technology. So they, instead of launching a single satellite, they launched 50 satellites. How did they do that? So basically, they have some central structure to which the satellites are connected to. And then once it's up in space, they just release one by one. This is the actual structure where you see the satellites mounted on. So it's really, it looks like something built in a garage to me, but it's really high tech. This is the satellite that was made by Space SI. So maybe, I have a close up here. It's really just a camera. So most of it is, so the dimensions of these are 0.5 meter times 0.5 meter. And most of the space is actually taken by this camera, which is some HD camera, which can take really exact pictures of the surface of the Earth. It's used for farming and estimation of damage in natural disasters and so on. And yeah, the part that I was interested in was actually this back part of the satellite, which are 4 small antennas. So you see, we're going from this 100-ton rocket to this, I don't know, few grams of material making these antennas, but still it's important to be able to simulate them, because they take really a lot of space, which is wasted because, yeah, it's not a lot of material there. And the idea was maybe to be able to bend them in some way, or maybe press them against the sides of the rocket and so on, or against the structure which was holding it, in which way it would, of course, reduce the amount of space, but the danger is that you only get one chance to do it. So if this would result in some sort of damage to the antennas, yeah, you're basically launching I don't know, dead weight, so it's not useful anymore. So yeah, you need to be sure that this will really be able to endure all those vibrations during the launch. So again, you need to use the beam theory that I was talking before. Especially here is important that you're able to control the dynamics of the end. So you have a complicated problem because you have dynamics, you have the motion, the vibrations of the rocket, which are moving the antennas, and then you have also the contacts if, for example, the antennas are hitting into the container and so on. This is my actual work. So I just I just added a small slide at the end about my actual work. So I'm focusing on contact algorithms. Basically, what I'm trying to do is to develop new algorithms, new techniques of how to detect if there is contact or not. So because when we have a mathematical model, it can do whatever we program it or whatever we tell it to do. So for example, if we don't have any contact algorithms, the material will just go one through another. It doesn't really know that it should stop. So we need a good contact algorithm which can detect and prevent this action. And this is what I'm working on. So it's really been, so this area of research is a little bit neglected by the community, maybe because it's really specialized, but nevertheless, compared to the other fields of contacts, the beam contacts are really under research for now, and this is probably why my project is also being financed. So yeah, I'm just making these algorithms more precise, more efficient. And the other aspect is the dynamics, which is really, so initially it was actually the main goal of the project, but now through the research, as it often happens, it was, at the beginning it was a lot of dynamics, some contacts. Now it's the other way around, a lot of contacts, some dynamics. It's the idea is to develop algorithms that will be able to monitor or to simulate beams for a long time, because the problem is that usually the algorithms are limited with the frequencies that occur in the simulation. So for example, if you have high frequencies, you usually try to simulate a short period of time, because so this is what you are limited with. Here we're trying to pass beyond these limits by introducing algorithms that are able to conserve energy and momentum of these beams, and in this way be more stable and yeah, numerically more efficient. I think this research is important from academic point of view because it's bringing new theoretical advancements, but also it has, I think it's nice because it has some actual applications in mind in the back of the hat, which maybe it will result in some advancements in actual projects maybe in a few years. So yeah, I like the research on it. So thank you for your attention.
Jan, from your presentation, we can guess you like your research. And from the last slide, we can see indefinitely research. Thank you for trying to present a really complex topic to the general public. So, questions, please.
No question. And before, when you showed how you model like the huge things wrapping around each other,
Okay.
and the other one, more complex one, actually how is the model built?
You mean this one?
Yeah.
So do you mean like, so we use finite element methods. You have two initially straight beams, which are discretized into smaller elements, so which are theoretically exact beams. So you have the center line, which is deformable, and you have rigid cross section. And so this analysis is quasi-static because so if you can neglect the dynamics of the problem, you can use the quasi-static analysis and really speed up the process. So yeah, this is one of the optimizations. So as I said, the contact is detected. So yeah, this is actually one of my research topics, to be able to detect contact not only at single points, which is how it was usually done, but along the entire length of the element. So for example, if you imagine that this is divided into, let's say, 10 elements, then along the entire length of this element, you still have a force. It's not only at the boundaries of these elements, not only in the connections. So what you need to do is to measure the distance from one element to the other, and then figure out if it is, so if you have the distance that is, so you measure away from the element. So if it is positive, then okay, then you don't have any penetration. If it is negative, then you have penetration, which you really don't want because you're trying to prevent it. So what we do is we apply forces using Lagrange multipliers, which are again distributed along the element. So how you do that is you apply some forces in the nodes, and then you interpolate between them, either linearly or quadratically. And yeah, that at the end is pulling the elements apart, in which way you see this effect of the contact. What the last thing that you need to be careful about is where to apply the contact conditions, because they usually work in a way that they will try to stick the elements together, which is good if you have penetration. Then this means that you pull the elements away and stick them together. But if they're initially away, this results in attractive forces, which you don't want. So you need to be able to say, okay, these parts of the beam are in contact and these are not. So this is another aspect. So you really need yeah, this to cover all these aspects to be able to have a good formulation. What I'm advancing or what I'm researching, what is new in my approach is this distributed contact instead of having point forces, which was the method that was just before.
Other questions, maybe? No. Thank you.
Sorry, can I ask a question?
Yes, of course.
I was just wondering, do you have any plans to validate this against some experimental benchmarks, or is that maybe already done?
At this point, we're still in the academic part of the research. So it's mostly the new contributions that are made are really focused on the precision of the model. So we don't really think about the experimental validation. This comes when you have when you're able to model larger scale problems. So to do this, you usually need some optimization and so on, specifically for that type of problems. So the left picture that you see, this is made by the company Centex Bell, and they actually compared the results of the models with the actual experiments. The things that I do are purely academic, and they for now their purpose is to be able to so you can theoretically validate these results, so you don't really need experiments for that.
Thank you, Jan. This is just so for your preparation and discussion. Thank you. Hvala svima još jednom što ste došli, što ste izdržali do zadnjeg predavanja. Bilo je odlično. Možemo.